This Zoom session is being brought to you by the fractal Eternity. All right. For today, we do 1.5, which discusses certain specific functions and their graphs, and 1.6, which is talking about shifting function graphs left, right, up, and down. All right, so various specific functions. The constant function, well, that's a classic, and its graph is a horizontal line at height, the constant. Just a second. Oh. Y equals x, identity function. Y is identical to x. Its graph is a diagonal line at an angle of 45 degrees. It goes through 0, 0, slope of 1. Y equals x squared is a graph of this U-shaped graph called a parabola. I mentioned it before. Square root of x is a parabola graph on its side and the upper half. Negative root x would be down here, and it would be, like I say, a parabola on its side. Y equals x cubed has this, what I call an N-shaped graph coming in from negative infinity, slowing down to a brief halt, then zipping on again. That's sort of like how I approach the toll plaza at the Bay Bridge. Just zoom in, stopping that fraction of a second, then zoom off. Okay, fine. Cube root of x, well, it's an inverse function, like the inverse. It's inverse of x cubed, and so its graph looks like this, flipped to a 45-degree angle. We'll be seeing more about that later. 1 over x graph, the reciprocal, has this graph, a curious quality that it, well, I'm showing a crossing line. That's an error. It never quite reaches the x equals 0 line because it zips off to infinity, and never quite reaches the y equals 0 line because you need an infinite value of x for that. So, okay, so there's that. This shape is called a hyperbola. Actually, this too is a shape you may not have heard, but you may not have known you've seen it, but you have seen it zillions of times. Namely, imagine a lamp near the wall and a light coming out of it, coming out in 2 cones. It'll make a hyperbola. The shadow on the wall will be in the shape of a hyperbola. Y equals absolute value of x is this V-shaped graph with a sharp corner at 0. All right, there are also what are called piecewise defined functions. This is a piecewise defined function. Absolute value of x equals x for positive x, negative x for x less than or equal to 0. Like that. Here we have, say, a function defined as 1 for x bigger than 1, x for x between -1 and 1, and 2 for x less than -1. So here is where, if for values bigger than 1, and this is a little bit off, it's constant. Between -1 and 1, it's this diagonal line, and for less than -1, it's this high horizontal line. Now you'll notice that here there's a break in the graph called a discontinuity. It's called a finite discontinuity or jump discontinuity because it's of only finite length. Here 1 over x has an infinite discontinuity at 0. Well, mathematicians don't really like piecewise defined functions or discontinuous functions. They're kind of inelegant. You have to consider multiple cases of everything. All right, so golly, I don't think I actually did any homeworks for this one. All right, we'll proceed. Let's move on. 1.6. To shift the graph of a function, just a second, you can add, if you have a graph y equals f of x, then if you, the graph of y equals f of x minus h, that quantity plus k, is a previous graph shifted left, right, up, or down. For example, take y equals absolute value of x like this. If you add k outside the absolute value sign, y equals absolute value of x, all that plus k, it shifts the graph up or down by k units. So this one is y is absolute value of x. Here'd be y equals absolute value of x plus 1. This one higher up is absolute value of x plus 2, more or less. This one shifted down is absolute value of x minus 1. This one shifted down 2 is y equals absolute value of x minus 2. Okay. Excuse me for a second. Now, so y equals f of x plus k shifts the graph up k units. Up if k is positive, down if k is negative. Now here we have y equals absolute value of x minus h. The minus h is inside the absolute value sign. Now this makes things happen h units later if h is positive. So it shifts it to the graph right if h is positive, left if h is negative. So for example, here's a graph of y equals absolute value of x. Y equals absolute value of x minus 1 is shifted 1 to the right. It's 1 unit delayed. Here's y equals absolute value of x minus 2. It's shifted 2 units to the right, 2 units delayed. Here's y equals absolute value of x plus 1. It's shifted 1 unit to the left. It's 1 unit earlier. And y equals absolute value of x plus 2 is shifted 2 units to the left. It's 2 units earlier. So y equals f of x minus h shifts the graph right h units if h is positive. Now notice a little difference here. Namely, if k is positive, f of x plus k shifts it up. If h is positive, y equals f of x minus h shifts it right. So there's a kind of a reversal outside and inside the function. And if you do both, f of x minus h, that plus k, shifts it right h units and up k units if h and k are positive, left and down if they're negative. So let's say here's a graph of y equals absolute equals f of x, then y equals f of x minus h plus k is shifted right h, up k to make this graph. For instance, now here we're going to multiply by multiply instead of adding and subtract. We'll multiply outside the function and inside the function. And as before, we'll do opposite things in perpendicular directions. So a f of x, that stretches, squeezes, or flips the graph vertically. If a is bigger than 1, and that's a vertical stretch, it's taller. Here's f of x, here's 2f of x, twice as tall. If a is between 0 and 1, it's a vertical squeeze, it's shorter. So here's y equals f of x, here's y equals half f of x, it's half as tall. And if a is less than 0, then it flips up and down. So here, this is y equals f of x, and here's y equals minus f of x. It flips up or down. As you can see, this goes up, then down, then up. This goes down, then up, then down. Excuse me. Yoshihara. All right. Now, so in y equals a f of x, you can say that a modulates the amplitude, the height of the thing. Now, amplitude, AM, amplitude modulation, does that sound familiar? Well, yeah, AM radio. AM radio works by, well, there's the radio tower sends out a megahertz or whatever radio signal, and the height of the radio wave rises and falls and rises again in accordance with the graph of the sound wave that it's transmitting. Now, the problem with AM radio is that when it's low, it's of lower power, and therefore the signal during this phase can be interfered with by natural electricity, lightning, or by radio or by electronic interference from electric devices, et cetera, et cetera. So AM radio tends to be a bit staticky, noisy, and so it's good for sounds which don't require the highest fidelity, human voice, for example. Now, y equals f of bx, I'll put the b in b times inside the function. This will stretch, squeeze, or flip, but horizontally, and reverse from what happens here. Here, when a is positive, it makes it taller. Here, when b is bigger than 1, it squeezes it horizontally. It runs through its cycle faster. If b is between, so for example, if here's y equals f of x, y equals f of 2x is shorter left to right. It runs through its range faster. If b is between 0 and 1, then that's a horizontal stretch. It runs through its range slower. So here's f of x. Here's f of 1/2 x is stretched left right, twice as tall. It's a slower function. And if b is less than 0, then it flips left and right. So if this is f of x, here's a graph of f of minus x. This flip left. So here f of bx, the b modulates the frequency, as an FM radio, which modulates the frequency of the signal. Here the signal is stretches out or squeezes in, or stretches out or squeezes in accordance with the sound signal it's sending. Now, the advantage of FM radio over AM is that it's at a constant amplitude, so it's not as vulnerable to interference from natural or human electrical noise. The difficulty is that it takes more frequency, a wider frequency range, aka bandwidth, and so they have to. So FM tends to be in the higher frequency range because there's more bandwidth up there. All right, now if this were the graph of y equals f of x, and y equals minus f of x is this, its graph flipped up for down. Here'd be the graph of f of minus x here, compared to this, flipped left for right. And if you do both, minus f of minus x, it flips left for right, then up for down. And that is a 180-degree turn. For example, if I take this, flip up for down, then left for right, that is the same as a 180-degree turn around the origin. So, for example, graph y equals the square of x minus 3. Well, if this is the graph of x squared, then this minus 3 means you move it right 3. So here's the graph of this. Here's the graph y equals 1 over x plus 4. 1 over x is this hyperbola reaching infinity when x equals 0, reaching 0 when x equals infinity. This plus 4 means you move it up 4. So this line here, called the asymptote, is raised 4 units. So it's asymptotic to x equals 0, but it's also asymptotic to y equals 4. Here, graph y equals minus the cube of x minus 2. Okay, we start with x cubed, like this. Here's its graph. Flip up for down, minus x cubed goes from upper left to lower right, with a bit of a stopping point in the middle. Really, I should make this more vertical. And then this minus 2 means we move it right 2, so it coming down, slows to a halt at x equals 0, and then continues going downwards. All right, now here we're given this graph. Goes through negative 5 by 0, negative 2 by 3, 0 by 0, 2 by negative 3, and 5 by 0. Nice and symmetrical. It's obviously an odd function. Graph y equals f of negative x plus 3, and graph y equals minus twice f of x plus 3. All right. If here is f of x, then f of negative x flipped it left for right, like this. Then plus 3 raises it by 3 units, so it goes looking like this. That's number 8. Letter B, here we go. Here's, we want to have minus twice f of x. So we take this and we flip it up or down and stretch it vertically. So this is the graph of minus twice f of x. And then up 3, its graph looks like this. Okay, sounds good. Let's stop recording.